Hey, Thomas.
Hey Luca, how's it
How are you
going?
doing? Good. I just got over jet lag, apparently. No, it's not really true, but yeah. A bit of it. Yes, it
Yeah,
is true.
well, that was quite a schedule. 1 week in San Francisco at GTC, which was great, and then
Yes.
1 week here in Europe, and then 1 week in the Catskills in New York,
Yep.
and then 1 week back. I'm pretty sleepy still too.
Yeah. But it was a great sequence of things to go through. The Catskills was a global offsite at Lightning. We had really a lot of fun. We posted some pictures on social. We are all in each of us had an Airstream trailer in this beautiful wood. And then there was a clubhouse where everybody could spend as much time as they wanted. And we ended up doing a lot of work, a lot of chatting, playing games. It was really nice.
Yeah,
So, yeah. Kudos to the organizers. Um, and we ended up optimizing a robotics model with Thunder, which was really nice. We got it. I'm using the Wii, the usual Wii. Uh, got it from, PyTorch was like 2.5 times slower than JAX, unfortunately. To be fair, it was a hand optimized JAX versus kind of best effort PyTorch implementation. But with minor modification and Thunder running through it, uh, we got it down to basically the same performance as JAX. So that was very nice to see.
yeah. Who
Uh,
doesn't like performance?
yeah, of course. And we learned how to measure it together as a team. So it was really nice. Um, I ate way too much, but it's good. It's back to normal now.
Yeah, and
All right.
all the wrong things, right?
Yeah, exactly. All right.
So
So what are we
here's
going
a
to?
picture of the place.
Oh yeah,
Right?
yeah. That
The
is cool.
downside is even in the American wilderness, you have keep off the freshly seed grass. Oh
Yeah,
yeah, and there you can
is
see the trailers in the background.
and the fireplace. Yep,
Fire.
exactly.
But yeah,
Yeah, good. So today we're going to do something that is a new thing for us, which is uh, after we were back, you had the idea of getting back to autograd in Thunder and turning it from a mechanism that appeared very early on in Thunder and was heavily inspired by JAX. So as you all know by now, Thunder has a autodiff engine or capability inside of it because and so we are integrating with PyTorch autograd, but we're not using autograd to compute the backward, and that is what allows us to roll out the backward and get a backward trace explicitly there.
right.
Uh, but it wasn't a transform, and then it was based on some delayed evaluation mechanism, kind of Jack style, and it was uh, swallowing some of the things we like, for example, annotations that we put on proxies, and so we wanted to see if it was possible at all to express autodiff as a transform, and a transform for us goes from valid trace to valid trace. So and
Yeah,
then you told me, recently you told me I got it done, and there was a draft PR, and this episode is the unveiling, the unboxing, the
yeah.
how they call it, the
So I
of
said
that.
there was a draft PR yesterday at midnight, approximately,
Exactly.
and so
So
yeah,
drum roll. Now you're gonna walk us through the
yeah.
thing.
We
Um,
we
how
promised
do we do
that
it?
the usual podcast is like is less rehearsed than the GTC talk. So yeah, we
Yeah,
can
that's a
we can
proof.
do the thing, right?
Yeah.
And And maybe readers remember still how the autodiff works. I think that was the very first Thunder Sessions episode, maybe,
Oh yeah,
or
yeah,
second.
yeah. One of the first or second. Yeah, we went through the formulas for backward for a linear, I think.
Yeah, so I start with 3. That's always suspicious. Let's start with. Okay, so let's say we have some function. And what's your favorite function, Luca?
Oh yeah,
We
that is
never
a trick
call.
question. Like Swiglu or
Oh yeah, Swiglu. How does Swiglu work? So torch,
yeah, I need to look it up.
and then what is the silo?
Oh, Silu maybe. Yeah.
Torch, and then functional silo A times B, right?
Yeah, let me check. Yeah, exactly.
So is that a thing? Torch, and then functional silo, or did I make it up? No, it's a thing.
It's a thing,
So
it's a thing. There's the DNN and the functional
very
thing.
good. Okay, so this, interestingly, like you see, it has 2 inputs, 1 output, and we may return to that. And then if we do, if we have A and B, so let's call it X, torch run, and let's just do 2. I never know what size to put here. And let's have it
Yeah,
require
just try.
gradient. And also the second input is of the same shape, right?
Yeah,
And
it's
let's
a
call it
unary function, so that would be good.
Yeah, so if we can call it,
Nice.
and we can try to do a Thunder digit function. And then we can do JFN XY, and nothing works. Ooh, 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 ooh. Yeah, I edited the comments here, and apparently I screwed it up, right?
Yeah, no worries. It's a draft after all, right?
Well, it's not pushed to GitHub,
I know, I know. I
but
know.
my idea was, instead of doing the comments like at home, we can comments as we go.
Oh, nice.
So we can, of course, use storage, autograd, and if we actually d-type torch float 64 for checking gradients, always use double precision, because that's really like and it will now work. The function object is not iterable. So how does, grad check.
Nice.
It returns true. So Thunder computes the gradient, and of course we know how to look at the gradient, and you will see the new gradient now, right? The new way of computing gradients.
Yeah.
So
That's the
Thunder
embedding I'm talking about.
last traces JFN, and we just want the last one, right?
Yeah.
Okay, so here it is. We have the silo function expanded here, but do you know it? It looks just the same. And the last backward traces also looks the same. So what changed? And if we want to know what changed, it's a bit of a pity that it's not completely made transparent, because our friends at NVIDIA, they have like the next great idea that will improve on this even further. So I will try to find. So this is this already the augmented? Yeah, this is already the augmented forward function. I will try to find the thing before the augmented forward. So this is also the augmented forward. And there is an error here. I can see it. But at some point, last traces, there's many of them, right?
Yeah.
Okay. So, and there is a thing that we aren't careful enough with not reusing the modifiable containers. But okay, so this is the forward trace before the autograd happens. And we can see that this is dead code elimination. That is maybe benign too. And this is another dead code elimination. Okay, and here we have the safe for backwards. And this is post autograd. So we want to take this one. Okay, so if we want to look under the hood, let's take this trace. And then there's a new Thunder, and I don't think we need this, transforms autodiff. And this has two functions mainly. And one of them is the grad transform on trace. And what it does the gradient transform. And here we have something that's actually interesting. And what we see here is that we don't see that much. And I had hoped that we see a bit more. But so this is the same old forward that we had before, the silo function. And now it has been automatically decomposed because there is no gradient for silo. And so it needs to go into the decomposition. If we
can change function, right? It's totally fine.
Yeah, so here's the silo. It decomposes to these bits. And we see these bits directly on the trace here. And then here we are at the output, T45. That is our output. We can see it here.
Yeah.
And the remainder is the backward. And it's a bit tricky where it comes from because the trace doesn't say.
Yeah.
And then it computes the backward trace, and this will be the backward. And it's assembled bit by bit from the backwards of these things. So the backward of neg A is neg of the gradient. So this is easy.
We could even probably annotate the trace if we optionally with what op is the backward of what, like, right?
Yes, and I think we could be a bit better here if we introduce an intermediate variable and say return C times B.
Yeah,
It would be the same, right? And but now we actually have 2 lines of code here.
Oh, nice. Yeah.
And
but still, I think it would be nice to have that info.
Yeah.
Is it captured in the object anywhere? In the underlying object?
Yeah, so this is in the bound symbol, and we could just add it to the bound symbols, the source into the bound symbols. We should do that. And it does that to some extent in the and we will see like why it's not working yet. Because actually the infrastructure does this, but there is a twist. and we will get to that. But
Yep.
so here's the backward that gets computed, and then there's a second step, and that's also in the, so this is the joint trace if you want, because it has the joint forward and backward. And of course, we can split this, and the splitting is a bit tricky. And the reason why it's tricky is because we have this get grad, which like gives us the gradient for one of the outputs, and it should only be the outputs that are gotten here. But there also are things that it just takes from above, right? So if we have mul here of A with something, we have A again here in the backward, and it will just be taken from there. And when we split it up into two things, we need to do this as the safe tensors that you know from Torch Autograd.
Exactly.
And so the other interesting.
This is just to remind everyone. This is because backward formulas basically depend on what they depend. So they can depend on something that was on a variable that was produced by the forward, or even by an input of the forward itself. So there are things that you just need to save to stick into the backward formulas, and we are seeing an effect of that. So there's the backward portion of the trace that depends on things that were defined in the forward, and then that's the thing.
And so the next thing we can look at is the split trace. This is another function that goes through the trace, and essentially it takes everything needed to compute the output and puts that in the forward, and everything else will be the computation of the backward. And typically it will be like starting from here, right? But depending on how the user writes their forward and backward, the gradient transform that we also had when we did the custom linear relu, the fusion kernels with Triton back in the day, in the last summer. And so here we see that it kept this upper part, which is this calculation, and then it has the lower part in the backward. And so it added the safe for backwards, and the safe for backwards contains all the tensors that are needed to compute the backward. And
can we also see it in the output of the forward, or not?
Yeah, we see it in the output of the forward here, right?
Yeah, exactly. These are the ones that are like sent out of the forward for them to capture them, save them, and pass them to backward. Yeah.
Obviously, like this is a grown mechanism, and nowadays maybe we would have these safe for backwards in this dictionary somewhere. But things are how they are, and so the kind colleagues at NVIDIA, they want to make this happen later, because here is another thing that we see. These are all elementary operations, but we've saved too many things for the backward, right? Ideally, the backward would only have like A and B saved for it, and not all the other things, because you can just fuse those into a kernel and then be done with it. Right? We don't have the fusion right here because it's not on the GPU. And usually this is done by a tricky rematerialization pass that checks whether there's something in the forward that is sent to the backward that could be fused in the backward, then it's not saved as a separate tensor and all that. And that would be a lot simpler if we could have fusion before splitting.
Yeah, you basically just say, okay, this operation, instead of computing it, is so simple that I can just recompute it in the kernel that gets fused, and I don't have to save it. That saves a lot of memory if you work with giant tensors. And the other thing is that now that we can reason about forward and backward traces, forward loss, backward traces, if you need to run the whole thing, you can also think about capturing the whole computation. So it opens up several opportunities for optimization. Something I wanted to mention here is that the conceptual simplicity of being able to capture and then create a trace for the backward in the same trace. So transform the forward trace into a plus backward, then cut it at the middle. This is like doable in a week under two conditions. One, you're Thomas. The second condition is that you're dealing with a functional trace. If this wasn't functional, right? If the computation trace wasn't functional and instead had crazy input types, complex stuff, you wouldn't be able to do any of this. So the importance of capturing your computation, doing a prologue that turns that thing into a purely functional expression, and then being able to operate on that functional expression, convert it to other functional expressions, where the boundaries of the functional expression, the prologue and the epilogue stay the same because they don't change. That's super powerful. And so that's why we need to be super diligent at keeping this functional, keeping the inputs be simple types as much as we can, because then it opens up a crazy amount of possibilities.
Yeah. And so one of the tricky bits in the old autograd was when you need to do the decomposition, how do you actually manage it? And so this is the nice part about this, is that the autodiff system, it liberally uses some utility functions, but the core of it is like 300 lines here. That's like the ouch, actually.
But, very disappointed, Thomas.
Yeah. But that was the jet lag. I blame it on the jet lag. But so the grad transform on the trace is the thing that does the first part that we saw, that it constructs the joint forward and backward. And so it uses a processor class that will see one bounce, and this is worth taking a look at. And so, unfortunately, like, this function is not in the best pedagogical order, but so here is the part that is the Python return, which is a bit thing and a bit messy, and we will gloss over it, and we will move directly to the cases. And so here we have constants for gradient, no grad required, right? If a thing doesn't need any gradient, then we can just keep the old bound symbol, and this is what's done here. Like, we add the process bound symbol, and then we set the result that it's the symbol output. This just means that in the new trace, we have the same thing as in the old trace. And so that's a very...
There's a funny comment on the synchronized thing. This is a really terrible hack.
Yeah, you can imagine who wrote this hack. But so the thing is that we had the episode on FSDP, and of course we love the FSDP, but so the FSDP actually inserts these high-level synchronization derivatives, and it uses the autograd forward-backward to replace it with altogether in the case of FSDP split tensors. And the trouble is that if you don't require gradients, and if you have LoRa, you don't require gradients on the main model's weights and only on this low rank path, then this would be constant for VJP. And so the proper solution probably is to have something that the symbol can say, I'm never constant. I want always forward and backward. And then it will put in the forward, it may put in the backward, and then it will be DCE'd if it isn't needed. That code eliminates like unused code. But so this is in the future. But so the next thing is there are actually two ways to define gradients, and this is also part of the legacy and building a system, like trying out new things and then discovering they work better, we want to keep them, and change things a bit. And obviously, this is needed for evolution. So this get grad fn and executor, this function that it gets here is actually the gradient transform that we had back in the day in the summer episodes on fused kernels with Triton. We defined a gradient transform for our new symbols. And these looked a bit like def gradient, I don't know, relu. I will make a fool out of myself. But def gradient linear relu. And it would take the same inputs, or matmul relu. Let's do matmul relu. And so it would take the same inputs as the old thing. So it would do C equals A and B, and the result is relu of A and B. And this would be Thunder Torch relu. And this will work. And then we need to define the gradient. And so the idea was that we define this grad C is prims thunder core prims get grad of C. And then we could take this is the gradient and we could use it to compute the we need the grad res, right? And we can use it to compute the gradient of C, and then grad C is equals, I don't know, thunder torch where C is greater than 0. And if it's not greater than 0, then it will be, or res is greater than
1 and 0.
This is the trick. And then it is grad C, and if not, it's thunder torch 0, like, or maybe you can even put a 0.0.
Yeah, that's what I was thinking.
I think that works, right? Mm-hmm. Or at least it's conceptually okay. B, and now I need to worry here. C T. I don't know. I think it is this way.
Whatever.
Right?
It's
And grad B is A
the symmetric of that.
C, because this will have the C has the same right dimension as B, so it needs to needs to be like this, right? And then this will be T times C, I think.
Yeah, I think it's totally fine if it's correct. Like
it's not.
It's fine.
It's not totally correct.
The concept is very clear.
But you'll manage.
Yeah.
And so this will be now the but I'm still not happy about it. But okay. Okay, and then you did thunder core prims put grad, and on A you put grad A, and on thunder core prims put grad B, you put grad B, and then you just returned res as if it was totally normal. So conceptually, this is the backward, and the other lines are the forward, right? And this is exactly the kind of function that we're calling here, and that we get here. And then the trick will be, and there's a case, this is like the old school way of doing it. And what you can see here is that I'm basically making this trick that I just showed you, that I made this grad transform here from the two parts that are forward and backward separately. But so if we have such a join forward and backward, we push a new scope. That means we start a list where we put the new bound symbols that we get from evaluating this thing, and then we just pop the scope. And this will give us the bound symbols in this new bsims list. It will give us the bound symbols of this thing here generated, right? And so I've split this up, except for the where, every line will be one bound symbol. And so all we need to do is split this up in the forward and the backward part, and the forward bound symbols we can immediately add, and we do this by adding processed bound symbols, which means I'm done with these bound symbols, put them in the new trace, and keep the metadata as good as possible, right? The tags and the source code lines, stuff like that.
So you basically say, okay, if I see a get grad or put grad, and the symbol, the name of the symbol is there in those. Sorry, if the symbol is in get grad or put grad, and the proxy names are within their arguments, then it deals with backward, and I put it in the backward bucket.
Right.
Otherwise, I put it in the forward bucket.
Anything you need a gradient for is in the backward. So this is a bit like more forward happy than that
was my question. Like you may end up adding more stuff to the forward, right?
Yes, but in the joint trace it is the position. In the end, in the joint trace it will be when you split it, it will be rearranged. So we may want to refine it to actually match the forward.
Probably you want to compute. You want to compute. To position backward in the joint trace, to position the backward symbols as late as possible. But you could also have a pass that does that, right?
Yeah. So the
after the fact, after you assemble everything, you make a pass.
So one thing we learned in December, if you want, is that reordering bound symbols is extremely dangerous for the memory compression. And so one thing we could do here is we could just say, well, anything that is not similar to what I have in the splitting algorithm, anything that's not needed for the output.
For the output, you put in the backward. Yes. I think
probably the better way, right, to do it.
Yeah. Otherwise, you pay a price with memory, probably almost invariably. No.
Well, probably there's cases where one or the other is better.
I think.
But maybe at some point we need to have like reordering with memory awareness, but not today.
Not today.
That's for a week without jet lag. But so the thing that I really think is totally cool is if we haven't found a gradient transform, we need to actually move down, and we saw this, that the decomposition got put into the trace. And so how this works is, well, we just grab the subsymbols and we put them into the unprocessed bound symbols. And so what?
Sorry, can you go back one sec? What is the case? If you haven't found anything that has recurve, or
if we
that doesn't have a formula. I see.
If we didn't find something that had the grad transform defined,
then you go down one level in the trace in the symbol definition, right? And
Right.
go to the
So
subset.
here, let's get the original. Here
Yeah.
we don't have something for silu,
Right, right.
so we do it like we take these guys,
One
and
level
so
down.
we have a queue, if you want, of the bound symbols that we want to process from the old trace. And so the trick here is that we put these to the front of the queue. When this is taken from the queue, but we can't do anything with it, we just push these to the queue instead.
Yeah.
And that's all the trick you need in order to descend into the subsymbols.
Yeah.
And to my
Pretty
mind,
nice.
that's like a very neat way to implement it.
Yeah.
Because the old way was, well, I must admit, I'm not that familiar with that piece of code because it was written by a colleague. And but to my mind, like this is a very simple thing. And also you don't have this, you don't go from trace to function to trace, which is always something that's a bit tricky, but you have this one function call that produces bound symbols here. When you call this function, it produces bound symbols that will then be processed. And all the other things don't really call functions a lot. And so, this this is not quite the story. Then at the end, when we see the return, we have written all the forward to the trace, and we have, and this is maybe also something to show here. This is like a funny assignment. And what this does is it puts the backward symbols in the front of this list, right? Because the last thing to compute in the forward will be the first thing whose backwards we want to do. And so then here, the backward is written in here, and we need to just put all the symbols that we collected for the backward there. And there is a good deal of bookkeeping around the getGrad and putGrad, because you basically, for all these that are intermediates, you need to eliminate the getGrad and the putGrad, and then you only want to keep the gradients for the original outputs. And for the original inputs, instead of keeping this putGrad symbol in the trace, what we did is add a thing to the return, which is cool because then the dead code elimination will see, oh, we need these outputs here, and you don't have a sync symbol, because a sync symbol is kind of tricky to handle because it doesn't really match with having the data flow represented in the trace.
Yeah.
And so that's the new style autodiff. It's a very simple autodiff if you want. And people always say, for like, when you want to understand neural network training, do write your own autograd. So this is my
Yeah, I mean, and again, like it's possible because we're dealing with functional stuff, and I think it's really neat how you then end up like cleaning up all the putGrad, getGrad, which are basically points of statefulness in a way, right? In your functional trace, and then you absorb them out.
So one thing that is there, if you use a thing twice in the forward, like we have this, do we use something twice in silu? No, we don't. But sometimes you use something twice. If I did this here and added A, then A is used here and A is used here. And the backward, if you want, of using a thing twice is adding things up. We see this in the backward graph, that we have these additions here. Well, actually, we don't see it in the backward graph because this is without using things twice. But let's do a simple thing here, like A times B plus A.
Yeah.
And if we have this, we see here that for the, which is the joint trace here, right?
We should totally render traces in math notation with LaTeX.
Sorry?
We should do a thing that renders pieces of the traces in math notation with LaTeX.
Oh, you mean instead of add, we do plus?
Yeah, no, we see the formula unrolling. That would be cool.
Yeah, so what you see here, the gradient for A is T15, right? And so T15 is obtained by adding the two components of the gradient. One is from multiplying A with the gradient of B, and the other one is like directly from the output, the T14. And so this is one of the bits of bookkeeping that eliminating the get grads needs to do, because you have two put grads, and the second put grad basically needs to add things. And then the thing that tricked me up at first is when there's a thing that is used as an intermediate but also returned, then you have only one put grad, but there is an implicit put grad there for the output argument.
Oh, wow.
Wow. Yeah, but so this is how
this
it all
super
works.
Cool.
And we promised, and I hope you appreciated the faux Italian title for this episode.
No, I haven't seen it.
Did you see it? Oh, no. This was a visit to the La Salumeria dell'Autograd.
Salumeria it's the, how do you call it? Like, it's the place where you buy the salami, the sausages, the prosciuttos, not the meat, not raw meat usually.
No,
they don't have meat. They only have the salami stuff.
I thought it was the place where the sausage was made.
No, salumeria is where you buy it, and maybe you make it in the back. Yes, yeah. But usually it's where you buy these things. When you make it, when the salami, you make it sausage in the salumeria, you make the salami somewhere else. So yeah, having autodiff transform is something that was kind of lacking there, and the whole design is now falling into place. So it's super exciting. I hope that we get it to prod as soon as we can. You mentioned that the whole test suite is passing right now.
No. Only
for the autograd test autograd. Only that.
Well, so there are a few tests that are specific to test the integration with autograd, and of course I tried to get them to pass first in order to.
Yeah.
Whenever there's a corner case, people made a test of it, and so the thing I mentioned where there's an intermediate that is also an output. This was one of the cases that I needed to fix because I didn't.
Of course.
Really get it the first time. But so currently, and the distributed tests fail because I tried to compute the gradient of a process group. And that, of course, totally bogus. And I need to fix it.
Amazing. Yeah, I'm super excited about this. And then there will be the collaboration with folks at NVIDIA that are also putting their attention on upgrading the autograd story. So I think it's beautiful. So
yeah,
great job. Very exciting moment of discovery for me. So I hope it was for other people too. I think we all deserve the weekend. And so let's collectively have a great weekend.
Yeah, so next Friday is Good Friday.
Mm-hmm. Oh, yeah. So we'll see each other in 2 Fridays. And then, and I wanted to mention I'll be at Paris PyTorch Day, PyTorch Day in Paris, PyTorch Day Europe, something like that, on May 7th. And I just submitted an abstract for a talk on Thunder, so I'll be talking around 20 minutes about that, and hope to have chats with people there. And yeah, super nice. And so see you in a couple of weeks. Have a great
Yeah, super awesome.
Easter break.
You have a good vacation.